Hello, everyone, and welcome to the Temporal Graph Learning Reading Group. Today we have the pleasure of Vahid Jalili, who is a computational scientist at the Broad Institute of MIT and Harvard, focusing on the intersection of machine learning, cloud computing, and computational biology. His work translates large-scale genomic data into personalized treatment strategies and has contributed to major platforms like Galaxy and the Anvil Initiative. Additionally, he researches machine learning applications within decentralized ecosystems with a particular interest in decentralized AI and graph encoding of blockchain data. And I think the last part leads very well up to your presentation today, Vahid. So take it away.
Yeah, absolutely. Thank you very much for the introduction. Sure. So uh, this graph we see here is, I don't know, you guys, do you see my mouse? Or sorry, okay. So this is a Bitcoin transaction graph. The green node here is a Bitcoin address, and the three letters are basically the first three letters of that Bitcoin address. The sphere that we see here is a group of transactions, and in this case, we have 35 transactions. And these dashed edges are basically a group of multiple edges connecting these multiple transaction nodes to this script node here. And in this case, we have 35 edges. So basically, just to walk over the visualization here. So between May 2012 and October 2012, this particular address received a total of about 22,000 Bitcoins. And this plot shows the distribution of those values. So many of those transactions, they were small, but they were a decent portion of those that they were like, hundreds of the Bitcoins or thousands of Bitcoins in each transaction. At roughly about the same time, between May 2012 and April 2013, another address, 1BB, received about 22 transactions, a total of about 47,000 Bitcoins. And this is the distribution of the Bitcoins it received in terms of, the edges. Most of them were very, very small amount, but a significant portion of those were over 1,000 Bitcoins per transaction. Then on April 9th, 2013, these two transactions transferred their entire balance of about 69,000 Bitcoins to this address, to 1HQ. This address didn't have any other significant inputs other than that 69,000 Bitcoins. Between April 2013 and 2021, in fact, it received 255 inputs, but the values were quite negligible, 0.15 Bitcoins only. And this is the distribution of the Bitcoins that it received. On the x-axis, you have the block height, and on y-axis, you have the Bitcoin values, which basically show that they're all very small. This address didn't have much other, transactions in terms of, sending Bitcoins to another address, except this one exception. It sent 101 Bitcoins to address 97F on April 2015. And there was really not much other happening on this address until November 2020, exactly at block 655,282. In this block, the entire transaction, everything that basically this script had, were used in a transaction. Um, Only one Bitcoin out of the entire balance was sent to an address BC1, and everything else was returned back to this address. And in the block right after that, so just 10 minutes after that, another transaction was initiated, and the entire balance of this script, Bitcoin script, was sent to another Bitcoin script to BC1, and 69,000 Bitcoins were transferred to this. So it turns out that these three addresses belong to individual X, and this address at the end, this one belongs to FBI. And here's the press release related to this case. But it turns out all these transactions that we saw, they were related to the Silk Road website, a notorious website that was involved in a lot of criminal activities. And it turns out that a lot of Bitcoins from Silk Road was also hacked by this individual X. So they basically stole from Silk Road. And this case and the graph that we saw was about collecting all those coins from individual X. Back then in 2020, uh, this was worth about $1 billion dollars of Bitcoin seized. And that was one of the largest law enforcement happened on the Bitcoin history. So the graph, just to take another glance at it, is like this. Obviously you could see that there are a few suspicious activities here. There are a significant number of transactions with very small amount of Bitcoin. There is like, one huge transaction happening. There are not much activities on anything else. So I think we kind of can guess that there is something suspicious going on here, but the reason that you're seeing it is because, I summarized it. I basically told you the story. I summarized a lot of, transactions that I only included transactions that were related to this, the transactions that were not related to I excluded them. I grouped some of the nodes and edges, so I basically simplified it. But the actual graph is this. And this is a huge graph. It involves a lot of nodes, a lot of edges, and and if you actually look at this graph, it's not that obvious there is something suspicious going on this graph. This is basically a same graph as many other graphs that you could see. And in this case, I just focused on that as transactions related to individual X. But if you take the entire Bitcoin graph, this will easily blend in with the entire Bitcoin graph, and you cannot really see anything hugely suspicious about this particular graph. So this underlines a few things. Like real world fraud is really complex. It has significantly evolving patterns. It's not like, you see a pattern that was used by individual X and the same pattern used everywhere. The patterns, they evolve. They use more complex patterns. And so you need to basically adapt. You cannot just basically take one pattern and then, search for that pattern across the entire network. You may not find a lot of hits in that case, because the patterns change over time. And another thing is, they happen over a very extended period of time. And in some cases, it's like, 5 years, 6 years that they happen in that period. So temporal aspect is hugely, hugely relevant here. But if you want to, take the entire window of 5 years transactions, you're looking at a huge graph. And another interesting thing is, you're not only looking at a graph that includes only, illicit activities. It is a mix of legitimate activities and illicit activities. So in this case, most of them are involved in the Silk Road. But in many other cases, many other transactions that you could see that they are basically totally legit transactions. Like someone sending thousands of bitcoins to another person, that doesn't necessarily mean it is an illicit activity. So this is just one example, this illicit activity, to show how complex is real world graphs, especially graphs that involve financial activities like Bitcoin. Um, and it is very important to correctly, efficiently model this kind of graphs and develop machine learning models on top of them. So, the paper I presented at NeurIPS, it basically aims to bridge this gap, between the data that you have and how efficiently you can use that in machine learning models. Um, Specifically in this one, the way that I tried to approach this problem was, I tried to model the flow of funds that are happening in the Bitcoin network. And I particularly tried to focus on, entity-entity relationships, deep flow of funds that are, transferred in the network. It's not just, 2 hops or 3 hops away, very long ones, like 8 hops, 9 hops away. Transaction context is really, really important. We will discuss that a little bit. So I basically try to also capture the transaction context and also the temporal context. And as I said, in the illicit activity case, you're looking at transactions that they happen over a very extended period of time. And so temporal aspect is really critical. So I talked about graph, an individual X. I showed it on a graph, but the fact is Bitcoin is not a graph. Bitcoin is blockchain. And graph-based modeling of blockchain, it happens to be, one of the most effective ones that, since early days of, research on Bitcoin, researchers, decided that graphs, they have such a huge potential modeling the system, the blockchain. And so many of the research, they are focused on the graph-based encoding, but that's not the only one. But here we're just focusing on the graph. And in fact, there are many, graph-based encoding of Bitcoin. or other, chains also, they're published, and two published this year. You can look at these graphs from various different perspectives. You can look at, at very, high level in terms of number of nodes and number of edges do you have, and then you can compare them. Some of them have thousands of nodes, some of them have billions of nodes. Or you can look at, you can basically compare them in terms of their scope. So in some cases, you're looking at the data sets that they covered the entire chain up to a cutoff point, of course. And in some cases, they are very focused on very particular application that they give only sampled sections of blocks that they are involved in the specific application that they're trying to address. So you don't have the full chain. You have, some windows on the chain. And in some cases, you are not only you're not just focusing on the on-chain data. You're probably focusing on off-chain. So in the last example that we have here, Bitcoin OTC, this one is well, it's not doing anything with the on-chain data. It is a graph of trades that happen on a peer-to-peer system of people trading bitcoins. The transactions were not recorded on chain, and it basically has nothing to do with the on-chain data. It is totally off-chain. So the approach that I basically took here, and I think one of the most, I would say, interesting aspects of that was I didn't actually start with blockchain and then look at how we can model that as a graph. Instead, I tried to keep modeling and the predictive power of the graph also in the picture. So it was a loop of develop the models, go back to the graph, go back to the modeling. In this case, I mean modeling. I mean like modeling the blockchain as a graph, and then iteratively improve this. And that led me to this graph. It is a heterogeneous graph. It has multiple types of nodes, multiple types of the edges, and they basically try to capture entity-entity relationships. They also try to capture all the contextual information you need, like transaction context. Transaction context could mean like in Bitcoin, some research are focused on if multiple addresses are happening at the same transaction, that means they're kind of related. So that kind of transaction context are important. Also the temporal context, I try to basically add to the graph. All the edges that are in this graph are time-stamped, and that is a very, very important aspect. We will discuss that a little bit. The graph is, to the best of my knowledge, is one of the largest publicly available graphs, 2.4 billion nodes and about 40 billion edges. In terms of size, it's about 4 TB. So it's a huge, huge graph that basically covers the entire chain. Um, you know this better than I do. Working with a graph of this size, it means you cannot basically take the entire graph and load into any model. It won't fit any memory, GPU memory or anything like that. So you have to, do, one of the approaches is basically you need to, select samples or communities of the graph and train your machine learning models on top of those, sampled communities. So one of the experiments that I had was, you can if you go through like common sampling methods like depth first search or breadth first search, some or random walks. Because of the nature of this graph, you may not, sample representative neighborhoods. And so I came across this forest fire sampling algorithm that Yuri Leskovic he developed a few years ago, 2006. It was a very interesting approach, and out of box, basically, that doesn't adapt to Bitcoin because of the heterogeneity of the graph, and the concepts that they're trying to model with different type of nodes here. So I basically adapted it to specifically to this case, and that is one of the features that comes with this paper and also this graph data set. And last point, the graph is huge. 40 billion edges. If you want to find, let's say, neighbors at 8 hop distance from a given script node, you cannot really parse through text files, TSV files, or anything like that. You definitely need, very effective solutions for exploring this graph. So this graph is also provided in Neo4j database. This is a specialized database for graphs, and all the sampling algorithms, all the querying and everything that basically happen on this, which is basically efficient. And you can get neighbors at 8 hop, 9 hop, 10 hops very easily. Okay, just a little bit of background on Bitcoin. So as you know, it is a blockchain, and excuse me, and each block has a section called metadata. There are a lot of information in the metadata section of a block, but two of the most important information here are block hash and the hash of the previous block. We know that roughly every 10 minutes, a new block is generated, and these two plots basically show that. This panel is the difference between the time difference between two consecutive blocks, and as you can see, it happens mostly around 10 minutes. I mean, I can explain the details why there are so much deviations here, but it's not very much um, um, obvious from the graph. And this is showing that basically the histogram of the time distributions. Again, like the we are looking at the mean of about 10 minutes per the time difference between two consecutive blocks. Um, and we know that with each block, there is a reward distributed. And this reward means you have the reward for mining, and that is the new coin generated in the in the chain. And this panel shows that new coins collected. And we know that, I mean, minting started from 50 coins per block, and it halves every 210,000 blocks. And this plot basically shows that there are a few dips like this, and I think this was bugs in the code that the miner used, and they didn't collect all the rewards that they could collect, and they missed some of it. And this is basically burned coins. But in addition to mining reward, which is basically the new coins that they were not in circulation, miners, they also get to collect a mining fee, and this is basically showing the miner fee. We could see those, having also in this mining fee. This is a sum of the of mining fee and also block reward, so the new transactions. Bitcoin blocks, they basically have any number of transactions. There are generally two types of transactions. One of them is the Coinbase transaction, that there is only one Coinbase transaction in the list of the transactions of a block, and it is always the first transaction. And there is also a lot of non-Coinbase transactions. So this block shows here um, the number of transactions, basically non-Coinbase transactions also in each block. We could see that in early days of Bitcoin, there were only few handful number of transactions per block. But moving forward, we could see that there are many, many, many more transactions, like thousands of transactions per block exist there. The interesting line is this line here that shows even today we see blocks generated that they only have the Coinbase transaction in it. And this happens when the miner succeeds in mining a block without including any transaction from the mining pool. Each transaction um, has um, has has outputs, and outputs is locking the scripts. They basically define the criteria or the condition that you need to satisfy in order to use the coins that they were locked. You need to show that you own the private key associated with the public key that is for that specific locking script. There are many different locking scripts, and this plot shows their popularity and how they gain popularity over time or how they drop the popularity. So this is the number. This is the list of different types of locking scripts that we have on the Bitcoin network. And the plot basically shows that in early days of Bitcoin, most of the transactions, basically all the transactions, they were of type pay to public key. And like moving forward, this type of locking script, it dropped its popularity, and pay to public key hash gained popularity. And I mean, we could also see that, in recent days, pay to public key hash is also dropping in popularity, and instead, pay to witness public key hash is gaining popularity. But overall, 44% of all transactions across all blocks are of type pay to public key hash. And the second is basically a pay to script hash here. So there could be any number of
Yeah, sorry
outputs.
to interrupt. Just a quick a naive question for the unlock script, how easy is it for someone to hack it to get access to the unlock script, or this is almost impossible?
Yes. So for some cases, you need quantum computers to unlock it,
Yeah.
to
So
hack
it
it,
is
basically.
theoretically it's possible. Some big companies theoretically have quantum computers that you can access it, but okay.
Yes, exactly. So it depends actually, locking the script. There are some locking script that they are not a standard. Like, the locking script says that if you can solve a specific puzzle, then you can, collect all the Bitcoins associated with that locking script. So that can be very easy. You need to think about, how to solve that puzzle and you can collect it. But some of them are really, really difficult if you want to take the brute force approach. You need, quantum computers to break them because they are based on the private key, public key,
Yeah,
cryptography methods that they are not easy to break.
I see. Perfect. Yeah, thanks for explaining that.
Yeah, thank you. So transactions can basically have any number of outputs. So this panel here shows the number of outputs that we have in the Coinbase transaction. So the plot basically says that throughout all the blocks, most of the transactions, they have only one output in the Coinbase transaction. So it basically means the miner is paying to only one locking script in the output. But there are patterns like this that they were common in the early days of Bitcoin, and this basically means, and I think this belongs to mining pools, that they used to pay the miners involved in that mining pool or the farm directly in the Coinbase transaction. So that's why you have like hundreds of addresses referenced in the Coinbase transaction. But moving forward, that pattern basically dropped in popularity. In terms of non-Coinbase transactions, again, this one was in the early days of Bitcoin, there were few outputs per transaction. But moving to more recent time, we see like tens of thousands of outputs in each of output scripts in each of the outputs. But we still see cases like this where you have only one output, and this belongs to many of the blocks that they just pay to one output in the transaction. So just to complete this puzzle, there is, in addition to outputs, there's also inputs. Um, Inputs basically refer to a previous output that was never used. So it's called UTXO, or unspent transaction output. The Coinbase transaction is the only exception here, that it doesn't have any input because it is not redeeming any coin that was previously generated. It is basically collecting coins that are minted in that specific block. So they are not, unlocking something previously generated. So that's why they don't have any input. But all the other transactions, they have at least one input transaction, and this is basically referring to a previous output. So there is this common, I think, misconception in looking at the Bitcoin transactions that we usually translate it as someone transfers some Bitcoins to another person. That is not usually what happens on Bitcoin. You've never transferred something from one address to another address. What in fact happens is you provide means to unlock something that was previously locked for you. So you are the only one who has the unlocking script. You can unlock it. And if you unlock that, let's say that you unlock about 10 Bitcoins, it is an atomic unit. So if you unlock it, you cannot use like a portion of it. If you unlock it, you have to use all of it, or you will lose it, right? So sending to someone basically means you unlock something, you unlock an amount of Bitcoin that you can unlock it only, and lock portions of it under locking scripts that the intended recipient can only unlock it. So if you want to send, let's say you have 10 Bitcoins and you want to send like eight Bitcoins to your friend, you need to unlock that 10 Bitcoins. You will create an output with an with a script that that only your friend can unlock it and associate 8 Bitcoins to that, and then create another output with the remaining 2 Bitcoins, such that you are the only one who can collect it. So that's how transfers basically happen because they are atomic units. You can only work with the unspent transaction outputs, and you only work with the locking and unlocking. So that basically what I explained is like transfer coins, and also, self transfers that you're basically collecting the changes in the transactions. So with that background, sorry, that was a little bit extended, long background on Bitcoin. So the way that we create a graph out of this is, let's say, we take a non-Coinbase transaction, and this one has one input and two outputs. We assume that we can associate input script with an address. We know the address. The address is A1. The output scripts. The output one is associated with A2 address, and output two is associated with A3 address. So we assume that we can collect these addresses. We can compute these addresses, and then we create a bipartite graph that connects every input to every output. So in this case, we will have one node, which is basically our input node, A1, and two nodes, A2 and A3, and there would be one edge from A1 to A2 and A1 to A3, so a bipartite graph. So I mentioned address, just a big parentheses here. Using addresses to represent scripts is a little bit simplification, and probably, sometimes a little bit oversimplification. You cannot determine an address for all the locking scripts. We have non-standard locking scripts that you cannot derive an address for them, or we have, some scripts that they have, multiple scripts inside them, so they need multiple signatures. And so in that case, you cannot, basically derive a single address that is representing that. So that is a limitation of this representation, that we skip some of the transactions. I will discuss about them at the end, but just to put in big parentheses about these addresses here. So for the Coinbase transactions, we discussed that there is no input in the Coinbase transaction. The only thing that we have is an output, and we assume that we can represent that output one with address 4. Well, we need to create a graph, and so we need to create a node that represents input. So we create a very special node called the Coinbase node, and this is one node in the entire graph. So there's only one copy of this, and it represents the Coinbase transaction. So at each block, this block basically shows the number of addresses in each block. So what this tells us is, if you take the block 800,000, at this block, we see about 2,000 or 3,000 addresses that are, or scripts that are generated in that specific block. Like, they were not referenced anytime before. So this means at every block, we're looking at generating or adding 3,000 new nodes to the graph. Or, in other blocks, we're looking at about 4,000 new nodes added to the graph, because these are the nodes that they were not created before. They are representing the addresses. The addresses were not created before. And so we are adding to the graph. So this basically shows you how fast this graph basically grows with every block that is generated at about 10 minutes. So every 10 minutes, we are adding at least 2,000 new nodes to the graph. The yellow line shows the addresses that were created before, but they are basically reused in this address. So it means you're not creating a new node, but you're adding new reference to that node. So basically, you're adding new edges to that node. So we're looking at about, in this case, we're looking at around 8,000 new edges, incoming and outgoing to different nodes added in each block. And again, we're adding every block every 10 minutes. So every 10 minutes, you're adding about 8,000 new nodes, 8,000 new edges to the existing nodes in this graph.
I have a quick question on this. Do you have some sort of idea on how many of the new nodes are kind of reoccurring people under the hood? Like, maybe they just got a new Bitcoin address?
Yes. Um, that is a great question. And that basically refers to wallets, not just scripts. So scripts can be unique, and they are pseudonymous, meaning that we don't know who's the identity behind them. But using multiple approaches, like clustering approaches, we can identify multiple scripts that they belong to the same person, and then we can associate that with a wallet. So in that case, yes, we can know um, whether an address that is newly generated, belongs to a person that had other addresses before, so that then you can associate them with a wallet. That is not what I do here. And as I said, I mean, in the beginning, some other, work, they do that kind of clustering. They cluster scripts based on the context that they usually appear in as inputs or outputs of the same transactions. And then they infer that those have, there is a common identity behind them so that a single person controls them, and then they associate them with the address, with the wallets, and they create nodes for the wallets. There are some, advantages and disadvantages to that approach. And one of the advantages is you tend to overcluster in some cases, and so you associate addresses to the people that they do not usually, belong to those people. And that was actually the reason that I'm not doing clustering. So I'm not, working with the wallets here. I'm working with the scripts that we know that they are unique. There could be like, in this case, like A1 and A2, they could belong to the same person. Like, A1 could be one of their addresses, A2 could be the other of their addresses. They could be like, belong to the same wallet. We don't know that. We're not doing that clustering. And wallet information is not recorded on chain. It is an off-chain computation, and it is not happening here. Does that
Okay,
answer the
thank you.
question?
Yes, yes. I feel like there's so much Bitcoin new knowledge, so it's really cool. Thank you.
Sure, absolutely. Thank you. Okay. Each edge has multiple attributes, but two of the most important attributes of the edges are how much BTC or Bitcoin is transferred in that, and also the block height. This plot shows the average BTC output in each transaction in the block. And well, we could see in the early days of Bitcoins, on average, the output scripts, they basically had like hundreds of Bitcoins transferred. But moving forward, we're looking at smaller quantities of the Bitcoins transferred in each edge. It makes total sense because in early days of Bitcoin was cheaper, compared to the fiat currencies. And today it is more expensive, and so the values have changed, and so that explains, why in early days you had a lot of bitcoins transferred in each block, and today you have fewer bitcoins transferred. But this is, I'll actually explain, one of the reasons about the edge point here. But let's look at this first. This is the sum of BTCs in each block, so how much you're basically transferring. And that gives us an intuition about if you look at multiple edges that they are co-occurring at the temporal domain, what you need to expect in terms of the BTC amount. So the BTC amount, it seems, it has kind of changed, but it is relatively around between 100 and 10,000. So it is a wide range, but it is basically not huge radical changes, but happening there in terms of the sum of the transactions. Uh, so uh, sorry, okay. Each script. So let me actually explain one thing here. So when you're modeling, the reason that I'm showing these is, when you're building a model on top of this, and you're taking an edge that belongs to early days of Bitcoins, you're taking another edge that belongs to more recent times of Bitcoins, and then you look at the BTC amount inside those, and that has significantly changed. And so if you do not, take into account the temporal aspect of that, you could easily confuse your model about what is happening in terms of the BTC amount. So your model could see like there were like hundreds of bitcoins coming in, and now suddenly you have like a little amount of bitcoins going out of a script, and then your model can misunderstand a lot of context there. So that basically explains it. But we will go deeper a little bit on that. So an input to a node, an input to a script basically means a UTXO is created. So someone created an output in a transaction that you are the only one that can unlock it. And so that results in an incoming edge to a node. And an outgoing edge from a node basically means a UTXO is spent. A transaction that was never referenced before is spent. So it means that you're transferring, quote unquote, to someone. But an important point here is uh, if you look at this graph like this, like an incoming edge is coming, an outgoing edge is created, and we are looking at a very wide temporal window, about 17 years temporal window, and you want to know, like, if an incoming edge comes, like it is created, how much, how long you need to wait until you can see an outgoing edge created. Like an incoming edge is created, and you're developing a model that, predicts whether an outgoing edge should be created or not. How long that model should expect for an outgoing edge to be created. That is a very complex aspect, and that's actually a very, very important aspect because, like, if you're building models like anomaly detection, or if you're building models that are related to market prediction, you need to know, when someone received some amount of Bitcoins and how long does it take for that person to actually spend that amount of Bitcoin. So there are a set of plots here that they basically explain that. So this shows the value of unspent mining reward. So it means the miners mine the block, so the Coinbase transaction, they generated an output and they never used that output. So that output has not been used, since they were created, right? So in the early days of Bitcoin, we could see, like, these, outputs created here. These are famously belong to Satoshi Nakamoto. He hasn't used them yet, and they are basically there. They are sitting there for one day to be used. There's this chunk of outputs that are created in early days again of Bitcoin. The miners created these and they haven't used them yet. So they are sitting there for over a decade and they haven't been used. We could talk about a lot about them. We could say that maybe they lost a private key associated with them and they cannot use it, or maybe they are saving them for another day or anything. We don't know it, but they aren't used yet. This is explaining the same thing, but only for the Coinbase transaction, sorry, non-Coinbase transactions. So the transfer coins only, not the minted ones. And we could see that, even from early days of Bitcoins, there are some, addresses that they received some amount of Bitcoin and they haven't used them yet. So this basically means there is an incoming edge created to a node and a corresponding outgoing edge is not created yet. So there is, like, over like 17 years temporal gap between when an incoming edge was created and its corresponding outgoing edge is not created yet. And this plot basically summarizes those two. We are looking at the cumulative. So the blue line basically shows the cumulative unspent minted coins. So it's basically explaining this one, that we could see that the early days, there was a huge amount of Bitcoins that they were created cumulatively. But moving forward, this kind of plateaued. It means that it is basically explaining this part here, that many of the coins, generated these days, they actually tend to get spent. And the orange line basically shows the ones that are spent, and the yellow ones are the unspent transfer coins, so they belong to non-Coinbase transactions. And this plot shows the temporal gap between when a UTXO was created and when it was spent. So the time difference between them, like, in terms of the graph, we're looking at the time difference between when an input edge was created and when an output edge is spent. And we're looking at it, this plot basically shows that most of the transactions are at around 1,000 blocks. So meaning that when an incoming edge is created to a node, a corresponding outgoing edge is only created after about 1,000 blocks. 1,000 blocks. So again, like, there's like 10 minutes temporal interval between each block. So it is like 10 minutes times 1,000. That's how much time you need to wait between seeing, like, on average, basically, a corresponding output and an edge created. So again, like, if you're modeling something that relies on edge prediction, in this case, you're looking at edges that are created at a temporal window of about 1,000 blocks. So this basically explains that we are looking at a huge temporal gap between what is happening on the chain. So the transactions created, and there's a huge temporal gap between a corresponding output transaction created. On average, there are some transactions, like, again, in this plot that we see here, that they are created and they are spent instantaneously. Like, they are created in one block and they are spent in the same block. We see those, but on average, most of them are at about 1,000. The second point is you know, uh, if you're looking at the temporal behavior of a script, of a specific script, or if you're trying to model the behavior of a specific person, like you're looking at the temporal behavior of individual X, what happened on, so the script and you can follow, you can walk on the graph with all the transactions. But if you're looking at, at the macro level, like, you want to know what is happening across everyone that are using, a blockchain, like everyone who is trading on blockchain, all the other transactions that are recorded there. Um, and if you walk on the graph, there is a huge temporal gap between them again. Like, you may need to go like, 8 hops or 9 hops on the graph in order to reach to a node that they have like, common ancestor. So like, I am doing some, trading on Bitcoin. Another person is doing it, at the same time, some other trading on the Bitcoin. And on the graph, since we are not related individuals. And if you walk on the graph, you need to go all the way to hop 8 or hop 9, to find a common transaction between us. And in that case, it will be hugely complicated and difficult for models to generalize to that, depth, to learn, the temporal correlation between the transaction that I'm creating and another person that is creating at the same time as me, but we don't have any relationship. To fix this, and I think the community has, good solutions, but in this case, what we're doing is, I create an anchor point, and I think also in some literature they call it as a shortcut node. So shortcut node or anchor point is basically a huge node that it basically tries to connect that events that are co-occurring on the temporal domain, but they are not necessarily related. So the individuals are not related, but or the addresses are basically not related, but they are happening at the same time. So it is basically trying to create a shortcut on the temporal domain. So in this case, you can easily walk on the graph with the help of this block node. Then you can make sure that you can reach the events that are co-occurring in the temporal domain within like 2 hops or 3 hops. You don't have to go all the way to 8 hops. So this is the overview of the pipeline that we have. Uh, so to get the information from Bitcoin, I use the application called Bitcoin Core. This is a reference implementation of Bitcoin. It was originally developed by Satoshi Nakamoto, and it is currently maintained by the community. So using that application, we traverse all the blocks that are on the blockchain, and then we extract all the information about the transactions, as we discussed, and then create a temporal graph. Then put that temporal graph in a temporal graph database, and then we develop all the sampling algorithms, as I discussed about, forest fire sampling algorithm. And then you can extract features, and those features basically, could be sampled communities. You have feature vectors for nodes and feature vectors for edges, and then you have different types of nodes and different types of the edges, and you have separate feature vector for them, and then you can start working with your machine learning models on top of that. For the temporal graph and the graph database, we are also providing them in batch TSV files and also a dump of Neo4j graph database. This is hosted on AWS Open Data. You can basically download it from there. And just for a quick start, like if you want to look at the hello world examples, things like that, I also created some pre-sampled communities in terms of some nodes and edges. But I highly recommend that if anyone wants to sample communities, they need to sample it specific to the application that they're working on. So if you're developing an application that is focused on a specific temporal window, like let's say that past year, you need to adjust your sampling algorithm to only do that. You're not interested to look at transactions that happened a few years ago. So, but this sampled community that is available on Kaggle and Hugging Face, these are just hello world examples, but you need to use your own criteria depending on the application you're working on. A few characteristics on the graph. So again, like it's a huge graph. In terms of edges, we are looking at about 40 billion edges. In terms of nodes, we are looking at about 2.4 billion nodes. There are different types of nodes and edges. The Coinbase node, as I mentioned, is just one node across the entire graph, but there are 3 other nodes. We talked about the script node and the block node. Block node is basically the temporal anchor. Transaction node I didn't cover here, but transaction node basically gives you it gives you contextual information. So The scripts that are usually happening at the same time, it could give you a lot of information. Like as I explained, like if you want to know the identity behind the scripts, like we want to associate them with the wallets, that kind of information, you need a transaction node to collect them, because then the transaction node, tells you which scripts they usually co-occur, and then based on that, you can decide whether you want to cluster them under a wallet or not. There are also, different types of the edges, and there are also triplets, different types of triplets depending on, the source node, the target node, and the edge type. Um, Comparing nodes in degree and out degree.
A quick question, if
Sure,
you don't mind.
please.
For the block node, how do you decide how many? Because to me, intuitively, it feels like block node are basically virtual nodes that people use on graph transformers, where
Mhm.
you used to sync information from different nodes. Potentially, mostly for like, global information, you will sync into a particular node in order for it to communicate across higher hop neighborhood and these kind of things. Um, how do you decide number of block nodes, and then how do you kind of go about that? Yeah.
Yes, absolutely. That's a great question. Thank you. So Uh, block nodes represent blocks. So for each block that you have on the blockchain, we create a block node for that. So we are not, doing anything like downsampling or deciding on dropping or including any blocks. So the cutoff point in this graph data set was 863,000, and that's why you have that many number of blocks. They're connected to every transaction and every script that is involved in that block. So that basically gives you a lot of contextual information on that. Block node, they have a lot of it is very feature rich node. It has a lot of summary information about the block. Some metadata information about the block, some summary statistics. Some of them I basically showed their plots, and there are also some plots also in the supplementary material of the paper. They are all metadata that are included in the block node. So it is a very feature-rich node, and for every basically block on the blockchain, we create a node. Does that
I
answer
see.
your question?
So block node is created per time granularity because you create
Yes.
one block per timestamp essentially.
Yes.
So this is a very unique type of node that we don't see in almost any other graph because you guarantee one node tied to one specific snapshot. And
Yes.
this node inherently have, well, it does have meaning, but it has no like concrete meaning. Like it's not a user or anything. It basically is just a tie to tie everything around the block together, which in a sense it's kind of like a hyper edge where you show that all these things are happening around the same time. They should be connected in some way, but this block is kind of an artifact to do that.
Exactly. Exactly. So HyperEdge actually was an area that I looked into it, and I think there was limited support for that in Neo4j. That was the reason I didn't go that direction. Um, but you're right. For every temporal point, there is one block node. So for every T, you have one block node corresponding to that. And I mean, as I said, also, the edges are also time stamped. So basically, it's kind of duplicated information. But the advantage of the block node is if you're walking on the graph, the edges cannot really help you that much. So the temporal attribute that you have on the edge is not going to help you, find the edges that are, walk on the graph on the related nodes, on the related edges. But this temporal node, block node, they basically, help you to walk. So it is very helpful in the sampling step that enables you um, to cover a set of transactions that are co-occurring. So you could say like 10% of all the transactions that are co-occurring, I want them to be included in the community that are sampling. That is the kind of applications that Blocknode provides.
I see. Thanks. Yeah.
Sure. So in terms of in degree and out degree, uh, script nodes and transaction nodes, as expected, they have a smaller in degree and out degree compared to block nodes. So, like again, like to our conversation, like block node, because it connects to every transaction and every script that is happening in that node, they tend to have a very high in degree and out degree. But the script nodes, they usually have very low one. And this plot also shows the correlation basically between in degree and out degree of every node. So like do nodes have higher in degree compared to their out degree? Like, are they receiving a lot of transactions and they are not generating a lot of output transactions? This plot basically explains that. But a very interesting point about this plot, and I like it a lot, is these two sections here. This shows that there are some script nodes that we actually don't see it here, that they tend to have very high in degree and out degree. So, in this case, we're looking at 10 million in degree and out degree. Um, these nodes, there could be many explanations about these nodes, but one of the common explanation about them that they usually belong to the exchanges, or they are like proxy nodes that people try to funnel their transactions through them. So, with the graph structure, I have a few minutes left, so I will be very quick. There are a lot of applications of this kind of graph data sets on Bitcoin blockchain. One of them, the easiest one probably, is if you're looking at graph neural networks and you're looking at benchmarking them at a very large scale. This graph is probably the largest one you can find. It includes all the real world transactions spanning over 17 years. No synthetic data. It is all real. And another aspect of that is, and this one I have seen quite a lot, that people tend to develop machine learning models on temporal data, and the data that they have, let's say it covers between 2015 and 2020, and they develop and train a model on top of that. And then when they develop into real world, they deploy it in the real world applications. It doesn't generalize that well because in real world in that temporal domain, there could be a lot of shifts in data in terms of data distribution. Like as we saw in the Bitcoin case, there are actually significant shifts in terms of number of transactions you have, in terms of the values of the transactions you have, in terms of the number of types of scripts that you have. So if you're basically trying to benchmark a model on the temporal domain, this gives you a lot of context. If it generalizes to this, you could safely assume that it will also generalize in the real world scenarios. Of course, you can develop, a lot of applications on top of this to do like, fraud prevention, risk assessment, and applications like that. Or you could also develop, personalized agents that they could do like, cryptocurrency assistance for you. But one of the interesting applications area for this is trained on-chain data, and on-chain, as we discussed, is pseudonymous. So basically, you do not know the real identity behind any of the scripts. But it is sometimes very important to know whether you can trust a script or not, whether you can receive or transfer bitcoins to them or not. It's called reputation system, and you can basically use this graph, develop a reputation system for each score for each node. You can associate it with your machine learning model can basically generate a score for each of the scripts. So that can be the credit score for that. And it has many applications. One of the applications is in under collateral lending. So if someone wants to borrow a Bitcoins, they could use that credit score to basically show whether they can trust them or not. And the third area, again, all this entire graph that we discussed about is specifically focused to on-chain data only, but there's also a lot of on-chain and off-chain information. Like one of the examples is market data that this is not recorded on chain. So someone transferred 50 Bitcoins, but you don't know what is the dollar equivalent of that. So that is off-chain information that is not recorded on chain. You can take this off-chain information from various different sources and then augment the graph, and that can give you a lot of more, significant powers. Like, you could do market prediction. Without off-chain information, you cannot basically do market prediction because you don't know the dollar value of those Bitcoins transferred. Also, if you're interested in like, socioeconomic studies, you can, take real world events, co-localize them with the events that you have on this graph. Like, block node is your temporal anchor. You can use that, and then you can see the real world impact, the impact of the real world events on trades that are happening on Bitcoin. This is my last slide. Sorry, we have a few minutes left. In terms of limitations, so as I said during when we were discussing about the addresses, uh, address is an easier and simpler way of representing a script, but it is not complete. So there are non-standard scripts. Some of them like OPT return. They are not, you cannot really drive an address for them. So this is a limitation here in this graph that they are not included in the V1. We're actually building V2, and that is solved in V2. Another point is, we are building a bipartite graph of each transaction, right? So, and we looked at the plots. There are some transactions that they have thousands of inputs and thousands of outputs. If you're building a bipartite graph from thousands of inputs and thousands of outputs, you're looking at hundreds of thousands of possible nodes and edges created there. And so then you cannot actually, put that graph in a sensible way. Like if you're creating batches of that, you cannot really put it in a sensible way in the GPU memory, and that's a limitation. That this graph is limited to only 25 inputs and 25 outputs. Anything beyond that is not included here. And the last point that I love to extend is to add more off-chain information. So this could be like market data. This could be like law enforcement reports in terms of the addresses they identified in the first example that I gave, like individual X. So that kind of information that could be added to the graph, so you know the real identity that was involved in an illicit activity, so you can use that to any fraud prevention or fraud detection that is happening on the graph. Okay, thank you. Any questions?
Yeah,
Yeah,
thanks for the thanks for the discussion. And yeah, please go ahead, Victor.
I was curious, in this V2, are there any natural projections that kind of make the Bitcoin graph easier to understand? Because when I'm thinking of Bitcoin, then I'm thinking of one person is sending Bitcoin to another person, and here we're talking about scripts and transactions and addresses. Is there any natural kind of projection or like reduction that makes sense and could be easier to work with for new people coming into this space?
Yeah, absolutely. That's a great question, actually. I like it. Um, you know, I think this is a way that we're trying to simplify that. So a node represents an identity, an input address, an output address, input incoming edge and outgoing edge to that. These represent TXOs, but you don't need to worry about the TXOs. So you can easily see, like, this is Alice transferring X amount of Bitcoin to Bob. So you could look at it from that perspective. And I think that is easier than looking from, UTXO perspective. And this is included in V1 and V2 as well.
Cool. Thanks.
Sure.
And I guess more for general question, if you want to play with, so you probably have no experience. If someone want to play with the entire data set, how much compute do they need? Um, Rough
Yeah,
estimates or yeah.
yes, absolutely. So um, I would answer it in two ways. One, if you want to work with the graph, meaning that you want to explore the graph, meaning that you want to create your own communities with the graph. You want to sample something, you want to generate your communities, you're interested in the activity of a specific person, you want to basically sample their activities, or you're interested in let's say the activity of a trading website that was active between, let's say, 2010 and 2011. So, this kind of specific applications that you have in mind. For that, you need to get the entire graph and then work with the entire graph and then sample the communities you're interested in. The graph, you need about 4 TB of storage to get that. And in terms of the memory and CPU, you don't have that much memory and CPU requirement. If it is, larger, it will be faster. If it is, smaller, it is okay. So that covers how you can work with the graph. But in terms of, how the kind of machine learning models you can develop on top of that has a different part, because you don't develop machine learning models on top of the original graph. You develop on the sampled communities, and the sampled communities, it depends on how you generated them. If you generated something at 8 hop, you're looking at each batch, you're looking at let's say, 100 sampled community. Each of the sampled community has tens of thousands of nodes. So you could probably go with a regular, standard desktop GPU to process that. But if you want to go, higher depth, like in terms of 12 hop neighborhoods, you're looking at larger memory capacity on the GPU.
Yeah, yeah, for sure. And yeah, and thanks for sharing that. I think that's also very helpful for people who might want to start play with it. And I think it's very exciting to have these large scale data sets come out. I know the current models, especially the more sophisticated ones, are very limited in scalability. And I think this is a good direction and good data source to have for people to benchmark and develop future methods that can hopefully scale to the 4 TB of data you have and put into production something in the future, right?
Yep,
Uh,
absolutely.
yeah, thanks.
Um,
I
if
also
I
have
can ask, oh yeah, sorry, go ahead.
Okay. First of all, thank you for the presentation. That was very nice. I work on fraud detection in financial networks, and I know that there are some special kind of patterns that we see. Especially, I have worked with simulated data like AML Word. But I want to know, since you have worked with this data a lot, have you seen any kind of these patterns that can be an indication of the fraud on the data?
Yes, that's a great question. Thank you for asking that. So I think you're referring to patterns like, fan in, fan out, sync nodes. Basically, there are a lot of, incoming edges to that node, and there's one outgoing edge to that node, or a chain of transfers that they basically try to obfuscate their transaction. So as I said in the beginning, there are many different patterns. So you can take each of these investigated fraud cases, and you can look at their pattern, and it will be really hard to come up with a single pattern that is common across all of them, because the patterns they basically evolve, they change, and they use different types of methods to hide their track. Hiding their track, coin join is one example of that. It doesn't necessarily mean someone is involved in something illicit. Some people are very active in trying to preserve their identity, and they use patterns that they sometimes you may incorrectly associate them with illicit activity. So, I think you need to take a far broader context of activities into account, and then you can, definitely develop something sophisticated. I mean, as I showed in individual X case, you're not looking at 3, 4 nodes. You're looking at a huge network of thousands of scripts involved, tens of thousands of edges involved, and so your model needs to really work with that. So if you're working in that area, and I think you can take this data set, and then you can sample communities, but in very high depth, like 10, 11, and then train your models on top of that. That can be very, very helpful. But a single pattern, I think that is very limited. Like fan in, fan out patterns, stuff like that. They are it is easy to put cartoonish drawing on those, but they don't really generalize that well in the real world setting.
Thank you.
Sure.
I have a quick question. So I think it's along the lines of what Andy asked about, like that it's a great opportunity for new people to work with this data. Assuming I have like a scratch space with 4 TB of data, is there any, like, now you mentioned that you spun it up with Neo4j and AWS? Is there any way that I can run some of this locally with like open source tooling, or am I at the mercy of cloud providers?
Yes, that's a great question. Neo4j has multiple licenses. So one of the licenses is their enterprise license. One of the solutions they offer is cloud-based solution. So cloud-based solution, unless you go with the paid versions, you cannot fit this graph on that. But they also have the community version. You can basically work with the community version. It is free and publicly accessible. And with that, you can basically start the graph locally, and you can work with that. You can explore that. You can generate your own communities. But if you're interested only, just getting a sense of this data set, how, machine learning models and everything you can create, if you scan this, there are a few notebooks that we created. They basically run on Jupyter Notebook. Data is pre-prepared. Data is on AWS Open Data. So the only thing you need is basically a Jupyter Notebook to run it. It doesn't need significant amount of resources. And that one, I think the application does clustering. So it tries to identify the scripts that are belonging to a wallet. And the testing for that is using one of the open resources available for basically, benchmarking the accuracy of data.
Do you know of any, or does anyone know of any open source like graph databases? I know that there was one called Kusu at some point, but I think that was archived. I haven't
Yeah.
looked into this.
There
I
are
was,
two great examples, I think. One of them is Neo4j. I mean, again, as I said, I mean, there's community edition that
yeah.
you can get it for free. Uh, there's a hosted version on the cloud. It is called AWS Neptune. So that one is a very, very powerful one. But I think they offer free versions with limited capacity. But if you can run it offline, I'm not sure. Like this data set, we also, share TSV files. So you don't need a graph database to basically work with that. But, working with TSV files, basically, you have to go through this TSV file up and down, multiple iterations. So it will be slow. But if you do not want to use graph database, you can basically use those TSV files. They are just huge files.
Yeah. Cool. Thank you.
Great.
Sure.
Thanks for presenting, and feel free to ask more questions. I do need to go to a different meeting, but thanks a lot for the presentation, and it was very nice to see this work.
Thank you. Thank you for having me.
Thank you.
Of course.
Thank you.
Thank you, guys.
Thank
Thank
you.
you.
Bye.
Thank you.
Bye.
Thank you,
Um,
Yvonne.
Bye.
Victor, really quick.